Okay, now it's yours.
Okay. Seems like there's a maintenance going on. I'm not sure will be interrupted later or not. So I will start the talk first. Today we will talk about the symplectic part of the story. And this is based on the discussion with Matilda last week and this Monday. So I briefly recall what we are doing last time. So first of all, we have our this and this with punctured. We want to associate some sort of invariant to the curves, the intersection between curves. So
excuse me, could I just say the title again, please, very briefly? Graded intersection of something.
Oh, okay.
Graded intersection number versus graded Floer cohomology.
Yeah, it's the same as last week.
Oh, okay.
Yeah.
Thanks.
Oh, I include a new reference. This reference is very good, found by Matilda. So they have all the background for Lagrangian, Lagrangian Grassmannian, and then Maslov index. Quite comprehensive, but a lot of detail you need to go through.
Thanks.
Okay, thanks. No worries. Yeah. So last week we talked about the deficiency of taking just geometric intersection number. We upgrade the geometric intersection number to some bigraded intersection number by looking at the intersection and then some tangent space. From here, we can obtain two number, call it C1 and C2. Let me call it R1 instead. R1 tilde and R2 tilde, which is in Z cross Z. Okay. So today, a bit of head up. We will give some sort of Z graded on the, let's call it C1 here and C2, on LC1 and LC2. Okay. So let's start with what we did last time. So let's say you have a punctured disc. So we have one AM action on it, half twist on the punctured, and so we with the number of punctured to be m plus 1. Okay. For example, this is like D4 and A3 acting on it. Let me let Edmund comes in. Okay. So continue. Then last time we introduced one object, the projectivization of the tangent bundle of our punctured disc. So we start with our disc, punctured disc, and then we look at the tangent bundle, and then we take the projectivization of this tangent bundle. Actually, in later, this will be seen as a Lagrangian Grassmannian. Wait, let me send Edmund the ID to come in. Sorry about that.
Maybe
do you have any question for the moment? I try send Edmund the ID and password.
Yeah, maybe we change. So this is only in dimension 2, because dimension 2.
Yep.
The Lagrangian Grassmannian is a U1 cross quotient by O2. So O2 is sorry,
is U1 quotient
quotient by
O1.
O1, U1 quotient by O1.
Yeah.
And then it's can you think U1 is circles.
Yep.
Right, and then the O1 is plus or minus 1, so it can treat as
RP1.
yeah, RP1. So this is, I mean, that's Grassmanning is, this is only true for dimension.
Yep.
Real dimension, I mean dimension 2.
Yep. Correct.
And in dimension 2, the every line in the tangent space is a Lagrangian subspace, and that's
Yes.
also only in dimension 2. Since higher dimension, if you arbitrarily choose any n-dimensional real subspace of the tangent space, then it might not be Lagrangian. Right?
Mm-hmm.
Yeah. Okay.
And this is covering. I mean, this covering may be is the same covering for the Maslov. This is we still have U1 a determinant square, right? So like here the determinant U1 just that. So there is a square map to this covering. Is that cross that covering? Is that so this covering is also only what is that working for? It's a local picture. So this probably is this bigraded. Is that only in dimension 2?
Is it only in dimension 2?
Maybe it look like only dimension 2. Otherwise, don't have this. You have two. You have covering group Z2 because of this homology of this P. Is okay.
Yeah.
So this isn't a local. It's for any points in the. It just this is respect to one point in the data. It's kind of local near the points in data. Because this covering depends on choice of one is this RP1 cross point, the other one is a point cross a loop winding around that particular points in data.
Yeah.
So this covering is it depends on this point in the data.
Right.
No, it's a global picture since it's not a universal covering. It's just a covering that by that covering.
But this depends on the points. That depend on points in the data.
Yeah,
no matter which point you choose, then if you choose a loop around that point, you lift to a I think it's the same number. If you choose different points.
But it will not be the same class in the H1. If you choose different points, it's not the same points in the H1 homology group.
No, it's not.
And then this covering, the covering depends on this cohomology class. So this particular cohomology class, which is on the RP1 is 1, 0. RP1 is 1. On this loop is minus 2, 1.
On every loop around any points in delta. I think that's
every loop. Oh, I see. Every loop. Okay. Okay.
Yeah, write down what Brian said just now.
Well, it's not dependent on point. It's every point. So this So this that two covering. Okay, sure. I was just misread there. Okay, so continue.
Yeah, to define this Z cross Z covering, we define a class in first cohomology, which is equivalent of giving homomorphism from the first homology to Z cross Z. And then this is the function we define. And this LW, so this LW is anti-clockwise around the puncture. Okay, I purposely call it a W. Later we will, when we go into the Riemann surface, we'll also use W as the root. Okay, any question of this for this setup? So last week we last week we also said that from this setup, what we got is for every curve, taking out the puncture. So for every curve, take out the puncture. And then if you look at the map, sending say x, go to txc, you take the tangent vector on it, and then there's a leaf. And we call this the is a bi-graded curve. Okay, and then from this bi-graded, you can, because we tell you how to leave the disk, and from this bi-graded number, you can find this grading. I call it grading. Okay, or local index if you look at the paper. Okay, and we will do the same setup for symplectic now. Any question? If no, then we move to the next section. Okay, so in symplectic geometry story, we are kind of moving into a higher dimensional case. Or you can see it as some Riemann surface. That's why we have symplectic here. Okay. Now I recall what we did a few weeks ago, a month ago. So what we have now instead is a symplectic manifold. This is omega, not W. This is omega, symplectic form. So what we take is a particular Mueller fiber. So I fix this W, fix the W, and I remind you what is this Mueller fiber is. It is just a zero locus of an polynomial intersect with a ball. Okay, and then what is this polynomial? This polynomial is the AM singularity polynomial. So I'll write it out. Because in AM singularity, this part is a SNM plus 1. But SNM plus 1 is non-degenerate. So to make it, SNM plus 1, if you look at this polynomial, this is degenerate. So to make it non-degenerate, we need to introduce this HW, which is the perturbation. So this HW is Sn plus 1 Wn xn. So picking the meaning of picking W hat is just saying that I'm picking the coefficient for this perturbation. Okay, and the symplectic form should be just the original, because this is called an exact. We use exact Lipschitz vibration, so this symplectic form is coming from some contact one form, some usual contact one form, but it's not important, so I don't want to write out the form now. Okay, so you notice that if you look at the zero locus of this or the roots of this polynomial is n plus 1 root. Okay, this is actually how we form our this. So my this is okay. So you take this polynomial and then fill all the point in. Okay. I think I need the square here. Not sure, but never mind. So the puncture of this is just the roots of this polynomial. Okay. You can also easily see that. It's n plus 1. Okay. So actually, these coefficients should be pretty small to make this thing transverse, so that this intersection is transverse. Okay. So what do we have now? So last time I told you that given this with some curves, let's see, you can associate a LC, a Lagrangian sphere. So this Lagrangian sphere should be like taking the zero section, taking the disjoint union of zero section. Okay, then each piece of it is the zero section in this Sn minus 1. Okay, and if you look at closely, take the SI here, look at the SI, they're actually in
the sigma is, do you mean by that the W hat,
W hat, W
that,
hat.
since this depends on that, right?
Oh yeah, it should be, yep, yeah. Yep. Okay, so where's this Lagrangian lie? This Lagrangian line lies in EW hat. Okay, and then EW hat actually lies in Cn. Okay, let me write it properly. So this space should be EW hat, which is our M, and then this EW hat lies in Cn, which also lies in Cn plus 1. Okay, this is the full picture of it. So far, any question? And I should also say a bit on the action. So just now I said that AN action add on this by permuting the puncture. So AN action on mural fiber is actually acting on the total fiber. So remember last time we talked about parallel transporting. So let's say this is the whole E. So I'll use another. Okay, use another whole E. Above this, this E has fiber, say EW hat, EW1, EW2, EW3, something like that. Okay, if you follow the parallel transport from this AN, you take the curve and then look at the twist, and then the symplectomorphism of this EW hat is the action on it. Okay, this is what we said last time. I just want to refresh. Okay. Okay. So now EW hat is our symplectic manifold. we look at a fiber bundle with the fiber Lagrangian Grassmannian over each point. Okay. So in the low dimensional case, you can think of that RP1. And note that Lagrangian Grassmannian is isomorphic to UN cross ON. And this isomorphism is given by because UN act transitively on LS, and then this is the kernel. Okay, the detail can be found in the book I gave just now, the reference. And actually, if you look at the determinant square map into U1 or S1, you can actually see that this is an isomorphism on pi1. So this is how you deduce UN over ON is isomorphic to Z. Okay. So now we know that pi1 of Lagrangian Grassmannian is Z. And actually, it is also the first homology of Lx since it is abelian. And we also get that H1 of LC of Z is also Z. Is it by some Poincare duo? Yep. So now we can, there's some class here called the Maslov class. But I will give a detailed formulation of this construction later. So this is some abstract construction now for now. So from here, we can get this the Z covering for this Lagrangian, no, for this fiber bundle by having every restriction to each fiber is a Z universal cover. I'll give a explicit formulation for this in a moment. Okay. After we get this, we also can get the grading for our Lagrangian submanifold. Okay. Any question with this setup? If not, I will give the explicit construction for this. This is possible. Okay. Okay, by assumption, our symplectic manifold is manifold with 2 times C1 of M, which is 0. But I'm not sure why we have this assumption. Did Brian know or not? Is it easy to see the mirror fiber has?
I forgot. I think there's some condition in the Maslov index. There's some computation involved.
Oh, okay.
Involve this assumption.
Okay. But never mind. Since we have this condition here, so if you look at the canonical line bundle over, so this, okay, so C1 of, so C1 should be describing the line bundle over EW hat. Okay. So if C1 EW hat is 0, that means the line bundle over CEW hat is trivial. Trivial meaning it's a trivial bundle. So it's like EW hat times a vector space. But now in this case, 2 times E1 C1 EW, the first Chern class of EW hat is 0. So we get that if I denote the line bundle to be K cross K is trivial. Okay.
K is the determinant of the tangent bundle. K is determinant of the tangent bundle.
Determinant line bundle.
Determinant of the tangent bundle, or maybe cotangent bundle. Maybe also that. So if C1 is 0, it's like a Calabi-Yau.
Okay.
So Calabi-Yau means you have a holomorphic volume form.
Okay.
And here that if you tensor it, I mean, if you square it, you have a trivialization. So maybe you need some volume form in the calculation.
Yeah.
We'll see where this is used.
Yeah. In a moment, I will say why I want this. So since this K cross K is trivial, so there's a non-zero section. Okay, non-zero section. So this non-zero section will help us to define a map. Define a map from the fiber bundle to U1 or S1. In fact, this is justifying why we can have this determinant square map into U1. And how is this defined? This is defined by sending the tangent space into DTC of dx bar wedge with U1 to UN. I haven't tell you what's U1 to UN, where U1 up to EN is an autonomous basis of DXL. So you first you have your try again. So you have your DXL. So you have LC. So you have X here. So you have T X. Yeah. Okay. So this implies this is well defined. I think this is what.
What is DGX?
Okay, DGX. Okay. So yeah, DGX. Okay, GX is this G is what is the G we take just now. So because this LC is coming from some G. So this G is what I used just now. This G here. Is the surface we use. Is the Riemann surface we use. And then DG is the differential of the G. Yeah. And then X is just saying at the X point. Yeah. But I will, in the moment, do a very explicit calculation using this to show how this is being used. Okay. Any question up to here? If not, then we continue. So to do this explicit calculation, first of all, we also want to introduce an equivalent formulation for the low dimensional case, which is this case here. There's one equivalent formulation for it. So let's start over again. So P is PT, the projectivization of my disk. And you can somehow also, with some trivialization, you also can see it as the space. Okay. So I consider this map here. Not that this is just a x1, right? Is it x1? Yep, x1. Oh, sorry.
Is C star quotient on the definition of the P C star? Okay, you change it. Okay.
Yeah. Sorry, someone want to do some maintenance. Can I stop for a while? I let him in first. Yeah, did Brian ask anything just now?
No, it's fine. It's fine. Yeah.
Oh, okay. So, okay, so this is like a S1 cross D as well. Okay, let's consider this map here. I claim that this map is actually representing the C. So what does it mean is it gives the same result as what C gave. So recall what C gave. So C sends PT cross lambda W to -1 and 1. And then send RP1 cross point 2, 1, 0. Okay. But note that this is lying in the no worries. The first homology of my space. Okay. So actually it's representing the winding number of the map. Is that correct? Okay. So let's examine what this map did. Okay. Let's say we consider this map first. So if you plug a point here, and then you plug a loop here, what this map is doing is this wrap around -2 times, inverse orientation, and 2 times. Okay, point is just a constant here. And then, okay, and then this is 1 time. Okay, this 2 times, this 1 time. How about this RP1? If you put the RP1 here, it did nothing
HZ.
here. Yeah.
What just can you remind what HZ?
Okay, HZ. Okay, HZ is actually the polynomial I used just now. If you want.
Is HZ. Okay.
Yeah. Is the polynomial that give the puncture, that have the roots as the puncture. This one, the perturbation. The perturbation. Where's the perturbation? This one. Yep. Okay. Wait, where is it? And then so if you plug your RP1 into this psi, so psi has no variable here, so this doesn't move, but this move. But remember, this is RP1, so you move twice is equal. You move is equal to move once in S1. That's why you got a 1 here. Okay, does it make sense or not?
Yes, exactly.
Okay, so the whole picture is like this. So the whole picture is like this. So you got this, and then you push it into P. Okay, by taking the do I write this correctly? Wait, you take the TSTZC and then you push it into here. Okay, and then there's a covering. This covering is just a covering of R with x1, which is by E2 pi I t. Okay, let's write it down. P2 pi I. Maybe write T1. That's PT pi I T2. Okay, and then what we did last week or at the very beginning, you can understand this covering space as the pullback of this map, this two map. Okay, and then the graded curve is here. Any question? So delta P appears here. Okay.
You know why choose this -2, 1? Is
why choose this -2, 1?
That,
the reason of choosing, I don't know. Oh, why choose this minus? Wait, let me think. Why choose this -2, 1? Oh, because one. Okay.
I know. Maybe make it cancel his.
Okay, these two should be the basis. Is it basis? Basis. Because if you do twice, you will do two. Okay. If you look, okay. If you look along LW once, so you are actually doing two RP1. Okay.
Yeah. Okay. Maybe they cancel this.
Yeah, the cancel. Yeah. Cancel the effect of RP1.
Mm-hmm.
Yeah. So 1 is 1 0, 1 is 0 1 actually. Yeah. Cancel the effect of RP1. Yeah. Yep. Because RP1 we count it as clockwise.
Okay, so maybe this map S is on the RP. This from C.
Mm-hmm.
Is C is a D remove data or C? What is C? Or C is the curve?
C is a curve,
right?
yeah.
Okay.
C is a curve, yeah. C is a curve. Right.
So yep. there is map probably D remove data.
D.
Do you have? Oh no, maybe not. Okay.
Yeah.
I send to. Okay, so the delta P, maybe delta P send all these point times lambda W. And the RP1 to point. There have to be two generators of this target. The target is to S1. S1 cross S1.
Yep.
So delta P maybe this combination is sent to the two generators. Lattice will be just a standard 1 0 and 0 1. Okay, and then take a look. Okay, I think this makes sense.
Makes sense. So yeah, so okay, the Z cross Z action on this covering space is just adding a constant function, which is what like we compute last time. Like this number is just some Z cross Z number. Okay. Okay. So next thing to prove to use what we did just now. Okay, now I want to introduce graded floor the grading on Floer Cohomology. So now we are proving lemma 6.17 in the paper. So first of all, let C be a curve that meet the punctures, which is something like this. C. So now trying to claim is I can get the grading of Floer Cohomology from the grading on topology. Okay. So any by grading C tilde of C, I can get canonically a grading LC of LC. Okay, from a curve I get a Lagrangian submanifold. From C tilde, which I know how to compute, I can get a LC tilde. Okay, and moreover, the formula is moreover, so the formula is if you have this kind of curve, okay, then what I get is just R1 plus N R2 on LC2. Okay, we will prove this. So proof. Okay, so now let us parameterize our curve. When we parameterize our curve, we throw away the puncture. So this is just an open subset. Parameterizing an open subset of C. And in that case, we look at the point on our Lagrangian, which is away from the puncture. So let S to be in EW head and also let and S is also a point in the zero section. Of my Lagrangian. Okay. So let's see. So what is this map here? So okay. So what we need to produce is something like this. So we have this from LC into U1. Okay. We want to. Hey, is this correct? Let me see. LC P delta P. Sorry, it's wrong. So sorry, it's wrong here. So should be going into L and then from my LC, and then I lift it into LC tilde. Okay, and then sorry, this is so this grading is called LC tilde. So this is should be a curly L here. This is a covering, the Z covering. Okay. So to show that I have this grading, this formula here, I should show that okay, let me write down. Should show show LC x equals to C1 okay. I want to show want to show this is actually grading of LC. Okay. So in my did I already explain the? Okay. So in the explicit construction just now, this map is taken to be e to the 2 pi I t. Okay. So e to the 2 pi I t should commute with this delta LC. Actually, I call it delta LC. Delta LC here.
You
Okay.
mean when
Yep.
you mean when restricting each to each fiber, then that covering is a universal covering corresponds to the R over S1 covering. So since this map e to the power 2 pi IT, it doesn't make sense since this
Okay.
L
I think I get what you mean. Yep. I get what you mean. So, yeah. Okay. So because now we are taking an X. Okay. So we're looking over the restriction over X. So that we can, so in every individual LX, we can look at this U and cross over. So that this map makes sense. Okay. Is other following?
You apply determinant square?
Determinant square is applied here. Here. So okay. So this should be agree with the determinant square map here. So that this is a lifting. So that this is a lifting of this LC. We want to show this diagram commute with this given map.
Then the determinant square should be a map from this curved L to S1. There is another map.
This curve X to S1. Let me see. Okay. So you mean something like this? X1 like this?
Yeah, then the e to the power 2 pi IT is the map over S1 from R to S1.
Okay, let me move this. Like this?
Yeah, that makes sense.
Then you pull back. L bar is a pullback of this map. It's like a pullback covering.
Yeah, correct.
There is a map. Yeah, that's correct.
Yep. Yeah, so this is some similar diagram from here. Yeah, so you can understand the covering space here as the pullback of this map. Okay. So let's do some computation. So, okay. So let's do, okay. So let's denote this as 1. And then this is 2. So we want 1 equals to 2. So what is 1? So 1 is actually just e 2 pi I on C1 to the gamma t plus and C2 to the gamma t. Okay, note that we just now already said C1, C2 is just some constant number. So we can rewrite this 2 pi I C1 to the pi I and C2. Okay, And then just now we show that this number here, this number in the previous setup in the low dimensional topology, this is commute with this. Okay, because this commute with this. So we actually get this formula here. Okay. Is everyone following? So using this map, apply on C1, C2. So this C1, C2 I apply, and then I get this because this commute. This is from last week construction, how I build a C1, C2. Okay, and then what I get is, so the first coordinate is HW on gamma t, since I parameterize the z as gamma t, minus 2. And then time the c. C is what? C is the tangent space. So it's prime t of square. Do I take square? Yeah, square. And then multiply by minus h. That is smaller. So minus h of w of delta t of n, right? I have n times. Okay. So in total, I get minus h delta t. W or not W is the same, and then minus 2 h prime t2. Okay. Now the next hop is to compute the determinant square to be this number here. Okay. So let me rewrite the formula again. Delta p tx lc, sorry, delta l is equal to determinant of g bar x with the orthonormal basis on the tangent bundle, tangent space of my Lagrangian. Okay, but to do this computation, right? Actually, it's depending on x, but maybe we look at one convenient x. Let's say we look at the North Pole. Okay, and then I think apply some differential geometry argument. You can see that all points should be the same number. So let's say this is the x we look at. So what is the differential of gx? So differential of gx is just t2 times xi bar txi bar, because I'm taking the bar conjugate in this setting. So I should be going from 0 to n plus 1. So you just do a differential and then times dx. And then the last bit will be h of gamma t, because I'm parametrizing the last coordinate. So by chain rule, you have d prime gamma prime t dt. Okay, this is what you get from differential of gx. And then to be convenient, pick this ei and up to en just as this dxi bar. Pick this as your ei to en. Okay, so let's mean I pick my ei and en is just dx 0 naught up to probably dx n minus 2 and then wedge dt. So the reason I stop at here because I'm picking this point. Is that right? Matilda, that's right.
No, because
No?
it's
Which one?
so this x is in
Uh-huh.
this x is in the north pole of a Sm-1 sphere. So you have only n-1 coordinates. So there is from 0 to n-2.
Like, how do I know which coordinate for me to throw away? Like, because I'm on the north pole, right?
Yes, it's this. So this x in the sphere. This sphere, what's the dimension? What dimension are you drawing?
Sn-1.
Okay, so this Sn
Oh,
actually,
okay. This is the 0 section, but this Sn-1's lie in Sn.
Yeah, that's why there is a direction of dt, and this dt direction is just the red one direction.
Okay. Yeah. So what she is saying is that okay, so so dgx is like going up. So for example, like if you look at this formula here, x squared plus y squared. If you look at the 0 set of this, it's like increasing circle. And the df is something like looking at the change of this 0 section, the level set. So df is, because if you look at the tangent space of these sphere is like this. So this df is like how to say, perpendicular to the tangent space. Okay, so yeah, so that's why we have dgx inside this formula. Makes sense to have dgx.
And the last one dt, in fact, should be gamma prime t
Gamma
dt.
prime.
Yeah, gamma prime t dt. Yeah.
Yeah. And then actually you can realize this. Then last time we say that this let me see, let me draw. So you have a tangent space here. So you can realize these bases, this vector as something like 0 dot 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 up to some point. You have minus h z to dot 0. Okay. So when you do this wedge product,
Then in that case, your basis should be should not be dx naught bar to dx m-2 bar. There are coefficient, the square root of negative h of that for each dxi bar. Right.
So
the last line, you're writing dx naught bar wedge. There should be coefficient since your point. Since your
wait, let me think. Okay, so are you saying that this dxi bar is equal to h? Oh, maybe some dei.
No. What I'm saying is that the basis you choose, you said that you choose a basis of dx naught bar wedge, but that's not a basis in the
tangent space.
Yeah, that's what I mean. And if you add the coefficient square root of negative h of that, then that basis is the basis in the tangent space of Sn-1.
So you're saying there's a scalar in front?
Yeah. For each. Yeah, that's what I mean. Since your Sn-1 is lying in the real n space spanned by span by negative.
Oh, okay. Okay, I think I get what you mean. So okay, because this dxi is coming from the original xi. So but in our construction, we said that these points are in the square root of minus hwz on r. Okay, that's why we introduce a constant. Is that correct? Yeah. So we introduce a constant. So let me write properly here. Introduce a constant. So this is gamma at a particular time gamma t. Okay. And yeah, this part is technical. So you pick the right basis and then you will get the answer you want. So what happened here is you only was left with one coefficient here. So this and this already cancel because you appear twice in your wedge product. And then this, you only pick out the last one. So, and also you evaluate your xi at this point here. So this point is also a square root minus hz point. So what you will get is determinant of c to multiply n times. So make sure I write the correct stuff. N minus 1 time. N minus 1 time because one of them I replaced by dt. So on my curves, so okay, let me say. So on my curve, I introduce one of the bases I take as the dt. Okay, so this is gamma t. So I already reduced one, so I have n minus 1. And then what else you get? You get gamma t. Okay, and then determinant of c of 2 times square root minus h.
There is no determinant here, right? Since
No determinant. Yeah, I already throw away. If I want the determinant here, I will put dx naught square onto dx and dt. Okay. So determinant of this thing is like just taking the coefficient. So and then what do I get? Square root. A bit long, so I should write smaller. Okay. So you combine the conjugate and then you're left with h delta t of n minus 1 gamma t. Let's say we already throw away the basis. So throw away the basis, I throw away the determinant. And then I squared it. Okay. And then what do I get? So I get a scalar multiply with this part here. Square root h delta t of n minus 1 square, wait, square gamma prime t square. Okay. Note that this number is defined to be in C star cross R 0. So this number is actually also equal to minus h gamma t n minus 1 gamma prime t squared. Okay, if you mod out the scalar, this is this number here. So you can see that actually this should equal to this number here. So we got this thing commute. Any question? Any question here?
That
Yep.
power, the h
Yep.
is power is a minus. I mean,
Which one?
a minus 2 is that a minus 1?
N minus 1. Let me see. N minus 1. N minus 1. Yeah, n minus 1. Hey, wait.
N minus 2 is
Where is the n minus 2? Oh yeah. So I already combined, so I should have n minus 2 left. I combine one of it with the conjugate. So is it? Yeah.
more.
So here should be minus 2. Okay. So there's n minus 1 of them. Wait. Yeah, n minus 1 of them. And then I combine one with the conjugation. And I left with n minus 2. Yeah, this should be n minus 2.
So what happened to this 2 times the power 4?
Oh, because
You have,
this element lies in C star cross R greater than 0. So
okay, so you take out that 30 is the reals. Okay.
so mod out by
Oh,
real
okay.
number. Yeah. Yeah. Okay. Okay, then then this number here. So this number will be used in the how you place the cohomology, the grading of cohomology in Floer cohomology, the grading of your chain complex. Okay, for example, maybe for example, so you take 2 Lagrangian. I just briefly say it. I won't go into much detail. So given 2 Lagrangian, if you look at the Floer cohomology of this 2, you should look at the intersection number, right? Okay, and then the intersection number will form the chain complex. Mod 2, we'll look at mod 2. And then the differential is this that satisfy the satisfy the equation, the du dx plus j du dt equals 0. And then you can see that there's intersection number here, right? Okay, and I can, so these things are coming from this, coming from curves, something like this, for example. Okay, so I can get local index here. And then this local index will transform into grading in Floer cohomology using the method, the lemma I proved just now. Okay. And that grading is the place you put your chain group. Yep.
Does that mean that there is some calculations in the Floer homology thing that can be done in the two-dimensional disk thing?
Say again. So is a Floer homology can be done in the.
So the lemma you just proved, there are two actions. One is on the Lagrangian LC0 LC1 thing, and one is on the disk. The curves.
Yeah.
So that means that you can calculate some numbers in the Floer homology just by counting the.
Yes.
Oh, okay.
Yes. That's the point. Yeah. That's the point. Yep. Yeah, that's the point. Yeah, that's the point. Yep. Yeah. Instead of going into the like. Yeah. So yeah. Correct. Yes. But of course there's a lot of detail I'm hidden from you. So I haven't tell you explicitly how the chain complex and the differential everything, even for the ungraded one. And I also haven't tell you how you're gonna use the bigraded intersection number through the algebra. Yeah.
So this which this is so you just finished the proof of the lemma 6.17.
6.17. Yep.
And then now, so this is what you just write. What is this? Can you what's the result here?
Oh, you mean what I wrote here?
This is just on the screen.
Oh yeah, this is the paragraph from 58, page 58.
Okay, so this so now the transverse. Okay. You mean the proposition 5.18?
Yeah. Yep. Yeah. So they define this absolute Maslov index. So the point of defining that is they want to get the the original lifting to be 0. That's why they put a half times n minus the dimension of the intersection. They already know that they can perturbate the Lagrangian submanifold, the intersection of Lagrangian submanifold, such that when they intersect, the dimension is n. So they define this absolute Maslov index to be 0 at those good Lagrangian, like transversely intersected Lagrangian. Because the Maslov index path would be also 0. Would be 0 in those cases, I think.
They're using some fact that this chain complex, this bond operator is 0. So then the Floer homology is like same as Lagrangian Floer homology, same as Lagrangian Floer chain complex.
Mm-hmm.
Do you want to stop somewhere the summary and?
Sorry.
Are you going to continue, or maybe you want to?
Yeah, stop
change?
here. Stop here.
But, oh, wait, okay, you want to stop here?
Yeah.